By the late 19th century, physics appeared to be a nearly complete science. For more than 200 years, classical physics built upon the laws of Isaac Newton, the wave theory of light, and later James Clerk Maxwell's equations of electromagnetism, had provided remarkably accurate explanations of the natural world. From the motion of planets to the behavior of falling objects, from sound waves to electrical currents, everything seemed to fit neatly into a unified and predictable framework. Many physicists of the time believed that the fundamental laws of nature had already been discovered, and that future work would only involve refining measurements and applying known equations to new situations. This confidence, however, was deceptive. Beneath the surface of success, classical physics was quietly facing problems it could not solve. These problems were not minor inaccuracies or experimental errors. They were deep contradictions between theory and observation. As experimental techniques became more precise, scientists began to uncover phenomena that simply refused to obey classical laws. These anomalies accumulated slowly, but by the end of the 19th century, they had grown into a full-scale crisis that shook the foundations of physics. One of the most troubling issues was the failure of classical physics to explain the behavior of energy at very small scales. Classical mechanics treated energy as a continuous quantity, meaning it could take on any value, no matter how small. This assumption worked well for large objects like planets, pendulums, and machines, but it began to collapse when physicists studied atoms, radiation, and microscopic processes. Classical theory assumed that matter and energy behaved smoothly and predictably, yet experiments suggested otherwise. A major source of concern came from the study of light and heat. According to classical physics, light was a wave, and electromagnetic radiation followed Maxwell's equations perfectly. These equations were among the greatest achievements of 19th century science, and successfully explained reflection, refraction, interference, and polarization. However, when physicists applied these same equations to understand how objects emit radiation when heated, the results were disastrous. The predictions did not match reality at all. This problem became especially clear in experiments involving heated objects, later called Blackbody radiation experiments. When an object is heated, it glows and emits light of different colors depending on its temperature. Classical physics attempted to describe this process using known laws, but the results were absurd. The theory predicted that as the wavelength of radiation became shorter, the amount of energy emitted should increase without limit. In other words, classical physics claimed that a hot object should emit infinite energy in the ultraviolet region, a prediction so unrealistic that it became known as the ultraviolet catastrophe. The ultraviolet catastrophe was not just a mathematical mistake. It was a clear sign that something fundamental was wrong with classical assumptions. Experiments consistently showed that energy emission peaked at a certain wavelength and then dropped sharply at shorter wavelengths. No amount of adjustment within classical theory could fix this discrepancy. The equations were correct, the mathematics was sound, yet nature refused to follow the rules that physicists believed were universal. At the same time, other experimental results were creating similar confusion. The stability of atoms was one such mystery. According to classical electromagnetism, electrons orbiting a nucleus should continuously lose energy by emitting radiation, causing them to spiral inward and collapse into the nucleus. If classical theory were correct, atoms should be unstable and matter itself should not exist in its observed form. Yet atoms were clearly stable and matter persisted. Classical physics had no explanation for this contradiction. Another troubling issue came from the behavior of specific heat in solids. Classical theory predicted that all solids should store heat energy in the same way, and that their heat capacity should remain constant regardless of temperature. Experiments, however, showed that at low temperatures, the heat capacity of solids dropped dramatically. Once again, classical predictions failed completely, especially when dealing with low energy or low temperature systems. These problems shared a common theme. Classical physics worked extremely well at macroscopic scales, but failed at microscopic ones. The laws that governed planets and machines did not apply to atoms, radiation, and energy exchange at small scales. This realization was deeply unsettling because classical physics was built on the assumption that nature is continuous and deterministic. Every effect had a precise cause, and every system could, in principle, be predicted with perfect accuracy if enough information were known. The growing list of failures suggested that this world was incomplete. Physicists were forced to confront the possibility that nature might not behave smoothly and continuously after all. Instead, it hinted at a hidden structure beneath reality, one that classical equations could not describe. This idea challenged centuries of scientific thinking and philosophical belief. The crisis was also psychological. Many leading physicists resisted the idea that classical physics could be fundamentally wrong. Some believed that the anomalies were temporary and would eventually be resolved within the existing framework. Others argued that the experimental data might be flawed. There was a strong reluctance to abandon theories that had been so successful for so long. After all, classical physics had powered the Industrial Revolution, explained celestial mechanics, and unified electricity and magnetism. Yet nature did not negotiate. The experimental evidence continued to grow stronger and more precise. Each failed explanation weakened confidence in classical assumptions and increased the urgency for new ideas. Young physicists entering the field were confronted with contradictions that could no longer be ignored. The belief that physics was nearly complete began to fade, replaced by a sense of uncertainty and intellectual tension. This moment in history marked a turning point. Physics was no longer a closed book, but an open problem. The crisis revealed that existing theories were approximations rather than ultimate truths. They worked well in certain limits, but broke down under extreme conditions. This realization prepared the ground for a radical transformation in scientific thought. The end of the 19th century, therefore, was not a time of completion, but of collapse and rebirth. Classical physics, once considered flawless, was exposed as incomplete. The very success of experimental science had uncovered its limitations. The stage was set for a revolutionary idea, one that would redefine the nature of energy, matter, and reality itself. It was within this atmosphere of confusion, contradiction, and intellectual desperation that Max Planck entered the scene. He did not initially seek to overthrow classical physics, but the crisis forced him to consider an idea so radical that it would change science forever. The failure of classical physics was not the end of physics. It was the beginning of a new era, one that would soon be called quantum physics. As the 19th century drew to a close, the crisis in classical physics became impossible to ignore. What made the situation even more troubling was that these failures were appearing precisely in areas where physicists expected their theories to be strongest. The laws of mechanics and electromagnetism were elegant, mathematically consistent, and experimentally verified in countless everyday situations. Yet, when pushed to extremes, very small scales, very high frequencies, or very low temperatures, those same laws collapsed. This contradiction suggested that classical physics was not universally valid, despite its long-standing success. One of the deepest philosophical assumptions of classical physics was determinism. According to this view, the universe functioned like a perfectly engineered machine. If the position and velocity of every particle were known at a given moment, the future could be predicted with absolute certainty. This idea was not only scientific but also philosophical, shaping how scientists understood causality, time, and reality itself. The growing experimental anomalies threatened this world, raising uncomfortable questions about whether nature was truly predictable at all levels. Another core assumption under strain was continuity. Classical physics insisted that physical quantities such as energy, position, and momentum could change smoothly, without jumps or interruptions. This assumption felt intuitively correct because it matched human experience at macroscopic scales. However, experiments involving radiation and atomic systems increasingly hinted that energy exchange might occur in discrete steps rather than continuous flows. This idea was deeply counterintuitive and seemed almost unscientific to many physicists trained in classical traditions. The crisis was intensified by the rapid advancement of experimental technology. Improved spectrometers, vacuum tubes, and thermal detectors allowed scientists to probe nature with unprecedented precision. These instruments did not merely refine existing knowledge, they exposed cracks in the theoretical foundation. Each new measurement acted like a stress test, pushing classical physics beyond its limits and revealing its weaknesses more clearly than ever before. Importantly, this was not a single problem with a single solution. The crisis was systemic. The ultraviolet catastrophe, atomic instability, and anomalies in heat capacity were not isolated puzzles, but interconnected symptoms of a deeper issue. They all pointed toward a failure in the way classical physics described energy and matter at fundamental levels. This realization slowly shifted the conversation among physicists from "how do we fix these equations?" to "what assumptions are we getting wrong?" The scientific community responded in different ways. Some physicists attempted increasingly complex mathematical corrections to classical theories, hoping that small adjustments might resolve the discrepancies. Others proposed speculative models that preserved classical ideas while introducing ad hoc mechanisms. These efforts, however, often solved one problem only to create another. The more classical physics was stretched to fit the data, the less natural and convincing it became. There was also a generational divide. Older physicists, who had built their careers on classical theory, were often reluctant to accept the possibility of a fundamental breakdown. Younger scientists, less attached to established ideas, were more willing to explore radical possibilities. This tension created a fertile intellectual environment, one marked by debate, skepticism, and creative thinking. Physics was no longer a discipline of certainty, but one of exploration and risk. The crisis extended beyond physics laboratories into broader scientific philosophy. If classical physics could fail so dramatically, what did that imply about scientific truth? Were physical laws absolute descriptions of reality, or were they merely approximations valid under certain conditions? These questions challenged the notion of science as a steady march toward final answers, and suggested instead that scientific knowledge evolves through revolutions as well as refinements. It is crucial to understand that this crisis did not mean classical physics was wrong in every sense. Newton's laws did not suddenly stop working, nor did Maxwell's equations lose their power. Rather, their domain of validity was revealed to be limited. Classical physics remained extraordinarily accurate for large-scale phenomena, but it was no longer sufficient as a universal theory. This distinction between approximation and fundamental truth would become a defining feature of modern physics. The emotional impact of the crisis should not be underestimated. Many physicists experienced genuine frustration and intellectual discomfort. The elegance and simplicity of classical theories had given them confidence and clarity. Now, that clarity was dissolving into uncertainty. Some even questioned whether the problems could ever be resolved, fearing that physics had reached a conceptual dead end. Yet, paradoxically, this sense of crisis was also a source of enormous creative energy. History shows that scientific revolutions often arise not from success, but from failure. When established frameworks can no longer explain reality, new ideas become possible. The collapse of certainty opens space for innovation. The crisis at the end of the 19th century was exactly such a moment. This environment set the stage for a quiet but profound transformation. Physicists began to suspect that nature at its deepest level might not conform to human intuition. Concepts like continuity, determinism, and absolute predictability were no longer sacred. Instead, scientists became open, sometimes reluctantly, to the idea that reality might be quantized, probabilistic, or fundamentally strange. The significance of this crisis becomes clearer when viewed in hindsight. Without it, there would have been no motivation to abandon classical assumptions. There would have been no reason to introduce radically new concepts. The crisis forced physics to reinvent itself. It was not merely a technical challenge, but a conceptual reckoning that demanded a new language for describing nature. Max Planck's contribution emerged directly from this context. He did not set out to destroy classical physics, but he was driven by the urgent need to explain experimental facts that classical theory could not. The crisis narrowed the range of acceptable explanations, making even radical ideas seem preferable to failure. In this sense, Planck's quantum hypothesis was not an act of rebellion, but an act of necessity. The collapse of classical certainty also prepared the scientific community, however reluctantly, to accept revolutionary ideas. When Planck introduced energy quanta, the idea was shocking, but it arrived at a moment when shock was already unavoidable. The crisis had weakened resistance to change by demonstrating that existing theories were insufficient. Thus, the crisis of classical physics at the end of the 19th century was not simply a historical problem. It was the essential precondition for the birth of quantum theory. It exposed the limits of human intuition, challenged deeply held assumptions, and forced scientists to rethink the nature of reality itself. What followed was not a minor correction, but one of the greatest intellectual revolutions in human history. The failure of classical physics did not signify the failure of science. Instead, it demonstrated science's greatest strength, its willingness to confront its own limits and evolve. From the confusion and contradictions of that era emerged a new understanding of the universe, one that would forever change how humanity perceives energy, matter, and the laws that govern existence. The Blackbody radiation problem emerged as one of the most serious and puzzling challenges in late 19th century physics, striking at the very heart of how scientists understood energy, light, and matter. At first glance, it seemed like a narrow technical issue related to heat and radiation, but in reality, it exposed a fundamental flaw in classical physics. What made the problem especially disturbing was that it arose from simple, well-controlled experiments involving heated objects, experiments that should have been easily explained by existing Theories: a blackbody is an idealized physical object that absorbs all electromagnetic radiation falling on it, regardless of wavelength or angle. It reflects nothing and transmits nothing, making it a perfect absorber. When such an object is heated, it emits radiation in a characteristic way that depends only on its temperature, not on its shape, size, or material. This universality made blackbody radiation extremely important, because it offered physicists a clean and reliable system for testing fundamental laws of nature. When scientists began studying blackbody radiation in detail, they noticed a clear and consistent pattern. As the temperature of the object increased, the total amount of radiation it emitted increased, and the wavelength at which the emission was strongest shifted toward shorter wavelengths. A warm object glowed red, a hotter object glowed yellow or white, and extremely hot objects emitted intense blue and ultraviolet radiation. These observations were precise, repeatable, and experimentally undeniable. The problem arose when physicists tried to explain this behavior using classical physics. According to classical ideas, the walls of a heated cavity could be modeled as containing countless tiny oscillators, charged particles, vibrating and producing electromagnetic waves. Classical electromagnetism and statistical mechanics were then used to calculate how much energy these oscillators should emit at each wavelength. The mathematics was rigorous and based on well-established principles, yet the results led to a shocking contradiction with reality. Classical theory predicted that the energy emitted by a blackbody should increase dramatically at shorter wavelengths. As the wavelength approached zero, the predicted energy output approached infinity. This implied that even a moderately heated object should emit enormous amounts of ultraviolet and higher frequency radiation. Such behavior was never observed in experiments. Instead, measurements showed that radiation intensity rose to a peak at a certain wavelength and then dropped rapidly at shorter wavelengths. The classical prediction was not just slightly off, it was catastrophically wrong. This dramatic failure became known as the ultraviolet catastrophe. The term reflected both the mathematical divergence and the intellectual disaster it represented. If classical physics were correct, everyday objects would release infinite energy, which was clearly impossible. The ultraviolet catastrophe exposed a fatal flaw in the assumption that energy could be distributed continuously among all possible radiation modes. Attempts to fix the problem within the classical framework quickly multiplied. Some physicists tried modifying equations or introducing artificial cutoffs to limit the energy at short wavelengths. Others questioned the experimental data, suspecting measurement errors. However, as experimental techniques improved, the data became even more reliable, and the mismatch between theory and observation grew more obvious. No classical adjustment could solve the problem without abandoning core assumptions. One reason the blackbody radiation problem was so disturbing was that it involved no exotic or extreme conditions. The experiments did not rely on rare materials or cosmic phenomena. They involved ordinary objects heated in laboratories, emitting light and heat in familiar ways. If classical physics failed here, it raised serious doubts about its universal validity. The problem suggested that classical laws, which worked beautifully for large-scale motion, were fundamentally inadequate for describing energy at microscopic scales. The failure also revealed a deeper conceptual issue. Classical physics treated energy as something that could be divided endlessly into smaller and smaller amounts. There was no minimum unit of energy. Energy flowed smoothly and continuously. The blackbody radiation problem hinted that this assumption might be wrong. The experimental results suggested that energy exchange between matter and radiation might be restricted in some way, although no one yet knew how. Another important aspect of the problem was its connection to thermodynamics. The distribution of blackbody radiation was closely related to temperature, entropy, and energy equilibrium. Classical statistical mechanics attempted to apply the principle of energy equipartition, which stated that energy should be shared equally among all available degrees of freedom. When applied to radiation, this principle led directly to the ultraviolet catastrophe. This meant that one of the most trusted principles in physics was producing nonsense results. This realization was deeply unsettling. Energy equipartition had been extremely successful in explaining the behavior of gases and many other systems. Its failure in blackbody radiation suggested that statistical mechanics itself might be incomplete, or that its assumptions broke down at high frequencies. The problem was no longer confined to electromagnetism. It spread into the foundations of thermal physics. As awareness of the blackbody radiation problem grew, it became a central topic of discussion among physicists. Conferences, journals, and private correspondence were filled with debates over possible explanations. Some believed that a new understanding of matter was needed, while others hoped that a subtle correction to classical theory would restore consistency. Despite intense effort, progress was slow and frustration mounted. What made the situation especially tense was the precision of the experimental curves. Measurements of radiation intensity versus wavelength produced smooth, reproducible graphs that classical theory could not match. The data did not fluctuate randomly or show signs of experimental uncertainty. Instead, they followed a precise pattern that demanded an equally precise theoretical explanation. The mismatch between clean experimental data and divergent theory was impossible to ignore. The blackbody radiation problem also highlighted the growing gap between theory and experiment in physics. For much of the 19th century, theory and experiment had advanced hand in hand, reinforcing each other. Now, experiment was leading the way, exposing flaws that theory could not resolve. This reversal challenged the confidence physicists had in their mathematical tools and conceptual frameworks. It is important to understand that the blackbody problem was not initially seen as revolutionary. Many physicists regarded it as a technical nuisance rather than a sign of a coming paradigm shift. They believed that a clever calculation or refinement would eventually bring theory and experiment into agreement. Few imagined that solving the problem would require abandoning the classical view of energy altogether. Yet, as time passed, the stubbornness of the problem made it clear that something fundamental was at stake. The ultraviolet catastrophe was not an isolated glitch. It was a warning sign. It suggested that nature behaved differently at small scales than classical physics allowed. The idea that energy exchange might be restricted or quantized began to emerge, though it was still vague and controversial. This growing realization transformed the blackbody radiation problem from a narrow research topic into a crisis of principle. It forced physicists to confront the possibility that their most basic assumptions about continuity, energy, and radiation were flawed. The problem demanded not just a new equation, but a new way of thinking. It was in this atmosphere of confusion, precision, and mounting pressure that Max Planck approached the blackbody radiation problem. He was deeply committed to classical physics and initially sought a solution that preserved its principles. However, the experimental facts left him with few options. The problem narrowed the path forward, making radical ideas increasingly unavoidable. Thus, the blackbody radiation problem served as the immediate trigger for one of the greatest revolutions in scientific history. It revealed the limits of classical physics with brutal clarity and created the conditions under which a new theory could emerge. The crisis was no longer abstract. It was encoded in experimental curves that refused to obey classical laws. As the Blackbody radiation problem persisted, it began to exert intense pressure on the scientific mindset of the time. The more carefully physicists examined the experimental data, the clearer it became that nature was following a rule that classical physics simply could not capture. The radiation curves were not chaotic or irregular. They were smooth, precise, and universal. Every attempt to force classical theory to fit those curves failed in the same way, diverging wildly at short wavelengths. This consistency in failure suggested that the problem was not mathematical incompetence, but conceptual blindness. The heart of the difficulty lay in how classical physics imagined the interaction between matter and radiation. In classical terms, the oscillators in the walls of a heated cavity could absorb and emit energy continuously. There was no restriction on how small an amount of energy could be exchanged. As a result, high-frequency oscillations were expected to absorb energy just as easily as low-frequency ones. When statistical mechanics was applied, this led to an equal distribution of energy across all frequencies, producing infinite energy at the high-frequency end of the spectrum. Nature, however, refused to cooperate with this logic. What made this especially puzzling was that classical theory worked extremely well for low-frequency radiation. At longer wavelengths, the predicted energy distribution matched experimental results closely. This partial success created confusion. If classical physics was fundamentally wrong, why did it work so well in some regions and fail so badly in others? The answer was not yet clear, but the pattern hinted that classical ideas were approximations that broke down under certain conditions rather than completely incorrect descriptions of reality. Some physicists suspected that the issue might lie in the nature of matter itself. Perhaps atoms and molecules did not behave like classical oscillators after all. Others speculated that electromagnetic radiation might have unknown properties that classical wave theory could not describe. These ideas floated through the scientific community, but none had a solid mathematical foundation strong enough to replace existing theory. The Blackbody radiation problem also forced physicists to confront the limits of analogy. For decades, physical understanding had advanced by comparing new phenomena to familiar mechanical systems. Heat was treated as motion, radiation as waves, and atoms as miniature solar systems. These analogies had been extraordinarily productive, but the Blackbody problem revealed their limits. Radiation inside a cavity did not behave like vibrating strings or water waves when examined at high frequencies. As frustration grew, the problem gained symbolic importance. It came to represent the growing gap between human intuition and the true behavior of nature. Physicists were accustomed to trusting mathematics guided by physical intuition, but now intuition itself seemed unreliable. The equations were internally consistent, yet they described a universe that did not exist. It is in this context that the significance of the Blackbody radiation problem becomes fully clear. The problem did not merely require a better formula. It demanded a revision of how energy itself was understood. Energy could no longer be treated as an infinitely divisible fluid flowing smoothly between matter and radiation. Something was preventing high-frequency modes from accumulating unlimited energy, and that something was not visible within classical theory. When Max Planck confronted this problem, he approached it with reluctance rather than enthusiasm. He was deeply committed to classical thermodynamics and believed strongly in the continuity of physical laws. His goal was not to revolutionize physics, but to preserve it by finding a formula that matched experimental data. However, the stubborn shape of the radiation curve left him with little freedom. Planck realized that if energy exchange were restricted in a very specific way, the ultraviolet catastrophe could be avoided. Instead of allowing oscillators to emit or absorb any amount of energy, he proposed that they could do so only in discrete portions proportional to the frequency of radiation. This assumption immediately suppressed the contribution of high-frequency radiation, bringing theory into agreement with experiment. At the time, this step was viewed as a mathematical convenience rather than a statement about reality. Planck himself regarded it as an act of desperation, something he later described as a formal trick. Yet, whether he intended it or not, the Blackbody radiation problem had forced him to break with one of the deepest assumptions of classical physics. The success of Planck's formula in matching experimental data was undeniable. It reproduced the observed radiation curves perfectly across all wavelengths and temperatures. For the first time, the ultraviolet catastrophe disappeared without artificial fixes or arbitrary limits. The problem that had resisted every classical approach was suddenly resolved. This resolution revealed the true nature of the Blackbody radiation problem. It was not merely about heated objects emitting light. It was about the structure of physical law at the most fundamental level. The problem exposed the failure of continuity and introduced discreteness as a core feature of nature. Energy, once thought to be infinitely divisible, now appeared to come in fixed units. The Blackbody radiation problem thus became the doorway through which quantum theory entered physics. It demonstrated, with mathematical precision and experimental certainty, that classical ideas could not describe all aspects of reality. The problem forced physicists to accept that nature operates according to rules that defy everyday experience and classical intuition. In retrospect, the Blackbody radiation problem stands as a perfect example of how scientific revolutions begin. It was rooted in careful experimentation, resisted by established theory, and resolved only through a radical conceptual shift. The problem did not announce a revolution openly. It quietly demanded one by refusing to be solved. Without the Blackbody radiation problem, there would have been no urgent reason to question the continuity of energy. Classical physics might have survived longer without challenge. Instead, this single issue exposed its limitations with such clarity that a new framework became unavoidable. The importance of the Blackbody radiation problem lies not only in what it revealed about radiation, but in how it changed the scientific attitude. It taught physicists that even the most successful theories are provisional, valid only within certain domains. When pushed beyond those domains, nature reveals deeper rules that require new ways of thinking. Thus, the Blackbody radiation problem was not an obstacle to progress, but the engine of transformation. It forced physics to evolve, setting the stage for quantum mechanics and reshaping humanity's understanding of energy, matter, and the universe itself. Max Planck's radical idea of energy, quanta, marked one of the most profound turning points in the history of science, fundamentally changing how humanity understands energy and the behavior of nature. At its most basic level, at the dawn of the 20th century, physics was dominated by classical ideas that treated energy as a smooth, continuous quantity. According to this view, energy could be divided endlessly into smaller and smaller parts, and physical processes unfolded in a continuous flow. Planck's proposal shattered this assumption and introduced a new way of thinking that no one had seriously considered before. Planck was not originally seeking a revolution. He was a deeply conservative physicist, firmly rooted in classical thermodynamics and strongly committed to the belief that the laws of physics were continuous and deterministic. His motivation was practical and specific: to solve the Blackbody radiation problem, which had defied all classical explanations. Experimental data showed that heated objects emitted radiation in a precise pattern that classical physics could not reproduce. Faced with this stubborn mismatch between theory and observation, Planck searched for a formula that would fit the data, even if it meant making an uncomfortable assumption. The radical step Planck took was to propose that energy exchange between matter and radiation does not occur continuously. Instead, he suggested that energy is emitted and absorbed in discrete packets, later called quanta. According to his idea, the energy of these packets is proportional to the frequency of the radiation, meaning that higher frequency radiation carries larger energy quanta than lower frequency radiation. This relationship introduced a new fundamental constant of nature, now known as Planck's constant, which sets the scale for quantum effects. This idea directly contradicted classical physics. In the classical world, there was no smallest unit of energy, just as there was no smallest possible distance or moment of time. Planck's quantization imposed a strict limit. Energy could change only in specific steps, not in arbitrary amounts. This was not merely a mathematical adjustment. It was a conceptual revolution. It implied that nature itself operates in discrete jumps rather than smooth transitions at the microscopic level. What made Planck's idea especially shocking was that it solved the Blackbody radiation problem immediately and completely. By restricting energy exchange to discrete quanta, high-frequency radiation could no longer accumulate unlimited energy. This eliminated the ultraviolet catastrophe and produced a radiation curve that matched experimental results perfectly. The success of the idea was undeniable, even to those who found it philosophically disturbing. Despite this success, Planck himself did not fully embrace the physical reality of energy quanta at first. He viewed quantization as a formal assumption, a convenient mathematical trick rather than a literal description of nature. He hoped that future developments would explain the results within a classical framework. However, history would soon show that the quantization of energy was not a temporary fix, but a fundamental feature of the universe. Planck's proposal also introduced a new way of thinking about the interaction between matter and radiation. Instead of energy flowing smoothly, atoms could emit or absorb radiation only when transitioning between specific energy states. This idea laid the groundwork for understanding atomic structure, even though Planck himself did not develop a full atomic model. The concept of discrete energy levels would later become central to quantum theory. The true power of Planck's idea became clear when other physicists began to apply it to different phenomena. Albert Einstein extended the concept of energy quanta to light itself, proposing that light consists of discrete particles, now called photons. This helped explain the photoelectric effect and provided further evidence that energy quantization was real, not just a mathematical artifact. What began as a solution to a single problem quickly grew into a new framework for understanding nature. Planck's radical idea also challenged long-standing philosophical assumptions about causality and predictability. Classical physics suggested that all physical processes could, in principle, be predicted exactly if enough information were known. The introduction of quantization hinted that nature might be governed by probabilistic rules at a fundamental level. Although Planck did not initially embrace this implication, it would become a defining feature of quantum mechanics. The idea of energy quanta reshaped the direction of 20th century physics. It paved the way for the development of quantum mechanics, influencing the work of scientists such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger. Technologies that define the modern world, including semiconductors, lasers, and medical imaging, trace their origins back to this single conceptual breakthrough. In hindsight, the true radical nature of Planck's idea lies not only in its technical content, but in its challenge to human intuition. The notion that energy comes in discrete packets is deeply counterintuitive, yet it reflects the true structure of the natural world. Planck's reluctant leap into quantization revealed that reality is far stranger than classical physics had imagined. Ultimately, Planck's radical idea of energy, quanta, transformed physics from a science of continuity to a science of discreteness at the fundamental level. It demonstrated that progress in science often requires questioning even the most deeply held assumptions. What began as a desperate attempt to save classical theory became the foundation of a new understanding of the universe, one that continues to shape science and technology to this day. Birth of the constant H. Planck's constant. Explain it in 1,000 words. The birth of the constant H, now known as Planck's constant, represents one of the most important moments in the history of physics because it introduced a new fundamental scale into our understanding of nature. Before its appearance, classical physics operated without any intrinsic limit on how small physical quantities could be. Energy, action, and motion were treated as continuous and infinitely divisible. Planck's constant changed this view forever by revealing that nature has a built-in granularity at the microscopic level. At the end of the 19th century, Max Planck was deeply engaged with the problem of blackbody radiation. Experimental measurements of how heated objects emit light followed a precise pattern that classical theories could not explain. When Planck sought a formula that matched the observed radiation curves, he found that existing physical constants were insufficient. Something new was required, an entirely new constant that would link energy to frequency in a way classical physics never had. Planck introduced this constant in 1900 while developing a mathematical expression that fit the experimental data. He proposed that energy could be emitted or absorbed only in discrete amounts proportional to the frequency of radiation. The proportionality factor in this relationship was a new constant, which he denoted by the letter h. This constant determined the size of the smallest possible energy exchange for a given frequency. In doing so, Planck unknowingly introduced the first fundamental constant of quantum theory. What made the birth of H so revolutionary was that it had no counterpart in classical physics. Classical constants such as the speed of light or the gravitational constant described the strength or scale of known forces. Planck's constant, by contrast, defined a limit to how nature behaves at small scales. It set the boundary between the classical world of smooth, continuous motion and the quantum world of discrete transitions. At first, H appeared as a purely technical parameter in Planck's radiation formula. Even Planck himself did not fully grasp its physical meaning. He regarded it as a mathematical tool necessary to fit experimental results, not as a deep statement about reality. Yet the presence of H changed everything. It introduced a fixed unit of action, a quantity that combines energy and time, signaling that physical processes at the microscopic level are constrained in ways classical physics never anticipated. The small numerical value of Planck's constant is crucial to understanding why quantum effects are not obvious in everyday life. Because h is extremely small, the discrete nature of energy becomes noticeable only at atomic and subatomic scales. For large objects, the effects of quantization average out, and classical physics remains an excellent approximation. This explains why classical laws seemed so successful for centuries before their limitations were revealed. As physicists began to explore the implications of h, its significance rapidly expanded beyond blackbody radiation. Albert Einstein used Planck's constant to explain the photoelectric effect, showing that light transfers energy in discrete packets. Niels Bohr incorporated h into his model of the atom, where electrons could occupy only certain energy levels. In each case, Planck's constant acted as the fundamental scale governing quantum behavior. The introduction of h also forced a re-evaluation of long-standing concepts such as continuity and determinism. In classical physics, systems could change by arbitrarily small amounts. With h, this was no longer true at the microscopic level. Physical processes were constrained by minimum units of action, suggesting that nature operates through discrete steps rather than smooth flows. This idea challenged deeply rooted philosophical assumptions about how the universe works. Over time, Planck's constant became a central pillar of quantum mechanics. It appears in the core equations of the theory, including the Schrödinger equation and Heisenberg's uncertainty principle. In these contexts, h sets fundamental limits on how precisely certain pairs of physical quantities can be known or controlled. The uncertainty principle, for example, shows that the product of uncertainties in position and momentum cannot be smaller than a value determined by Planck's constant. The birth of h also marked a shift in how physicists understand measurement itself. It revealed that observation is not a passive act, but one constrained by the fundamental structure of nature. Measurements at small scales are limited not by technology alone, but by the presence of Planck's constant. This insight reshaped experimental physics and the philosophy of science alike. Today, Planck's constant is recognized as one of the most fundamental numbers in physics. It defines the scale at which quantum effects become dominant and serves as a bridge between energy, frequency, and action. Its introduction signaled the end of classical physics as a universal theory and the beginning of a new framework capable of describing the microscopic world. In retrospect, the birth of Planck's constant was not just the introduction of a new number, but the discovery of a new principle of nature. It revealed that the universe is not infinitely smooth at all scales, but structured in a subtle and profound way. From this single constant emerged an entirely new understanding of reality, one that continues to shape modern science, technology, and our view of the universe itself. The initial resistance from the scientific community to Max Planck's quantum idea was intense, widespread, and deeply rooted in the intellectual traditions of classical physics. At the beginning of the 20th century, physics was built upon concepts that had proven extraordinarily successful for centuries. Continuity, determinism, and causality were not just technical assumptions. They were foundational beliefs about how nature itself operated. Planck's proposal that energy could be exchanged only in discrete units directly challenged these beliefs, and as a result, it was met with skepticism rather than celebration. One of the main reasons for this resistance was the dominance of classical physics. Newtonian mechanics and Maxwell's theory of electromagnetism had explained an enormous range of phenomena with remarkable accuracy. From planetary motion to electrical circuits, these theories worked so well that many physicists believed they represented final truths rather than approximations. Against this background, the idea that such a successful framework might be fundamentally incomplete seemed almost absurd. Many scientists saw no reason to abandon continuity and smooth change in favor of an unfamiliar and counterintuitive concept. Another source of resistance was the conservative nature of scientific thinking itself. Scientific progress often relies on extending existing theories rather than overturning them. Planck's energy quanta did not emerge naturally from classical principles. Instead, they appeared as an abrupt break. This made them difficult to accept, especially because Planck initially introduced quantization as a mathematical assumption rather than a physical necessity. Without a clear physical interpretation, many physicists viewed the idea as artificial or even unscientific. Ironically, Max Planck himself contributed to this resistance. He did not immediately argue that energy quanta were real physical entities. Instead, he treated them as a formal device to reproduce experimental results. This cautious stance influenced how others perceived the idea. If the originator of the concept was hesitant to claim its physical reality, it was easier for critics to dismiss it as a temporary trick rather than a genuine insight into nature. There was also strong philosophical opposition to the idea of quantization. Classical physics was deeply intertwined with the belief that nature is continuous and deterministic. The suggestion that energy could change only in fixed steps seemed to introduce discontinuity into the fabric of reality. For many physicists, this was not merely counterintuitive. It felt like a retreat from rational explanation. They feared that accepting quantization would undermine the predictive power and elegance of physics. Experimental skepticism further fueled resistance. While Planck's formula matched Blackbody radiation date extremely well, many physicists hoped that an alternative classical explanation would eventually emerge. They believed that better experiments or more refined calculations might eliminate the need for such a radical assumption. As long as quantization appeared in only one narrow context, it was easier to regard it as an anomaly rather than a universal principle. The resistance was also shaped by generational differences within the scientific community. Senior physicists, whose careers had been built on classical theories, were often the most skeptical. For them, accepting energy quanta meant questioning the foundations of their life's work. Younger physicists, though more open to new ideas, were still cautious, as adopting such a radical concept carried professional risks in a conservative academic environment. Another factor was the lack of a broader theoretical framework. At the time of Planck's proposal, there was no quantum mechanics, no atomic models based on quantization, and no clear way to connect energy quanta to other physical phenomena. Without such a framework, the idea appeared isolated and incomplete. Scientists prefer theories that offer unity and explanatory power, and Planck's hypothesis initially seemed too narrow to fulfill that role. The resistance began to weaken only when independent evidence for quantization started to appear. Albert Einstein's explanation of the photoelectric effect in 1905 provided strong support for the idea that energy exchange occurs in discrete units. Even then, Einstein's work faced skepticism, and many physicists accepted his results while rejecting his interpretation. This selective acceptance shows how deeply entrenched classical thinking remained. As more phenomena, such as atomic spectra and specific heat anomalies, were explained using quantization, the scientific community gradually shifted its position. What was once seen as a desperate assumption began to appear as a fundamental principle. However, this acceptance was slow and often reluctant. The transition from classical to quantum thinking was not a smooth evolution, but a painful intellectual struggle. The initial resistance to Planck's idea highlights an important truth about scientific revolutions. Even the most transformative ideas are rarely welcomed at first. They disrupt established beliefs, challenge professional identities, and force scientists to rethink concepts they once considered secure. In this sense, resistance is not a failure of science, but a reflection of its deeply human nature. Ultimately, the rejection and eventual acceptance of energy quanta demonstrate how evidence, persistence, and new perspectives can overcome even the strongest opposition. What began as a controversial and unsettling proposal became the foundation of modern physics. The resistance Planck faced did not diminish the importance of his idea. Instead, it underscored just how radical and far-reaching his contribution truly was. The foundations of quantum mechanics represent one of the most profound shifts in human understanding of nature, redefining how matter, energy, and information behave at the most fundamental level. Unlike classical physics, which describes the world in terms of continuous motion and definite properties, quantum mechanics emerged from the realization that nature at small scales follows rules that are fundamentally different from everyday experience. These foundations were not laid by a single discovery or individual, but through a series of conceptual breakthroughs that collectively reshaped physics in the early 20th century. At the heart of quantum mechanics lies the idea of quantization. Energy, momentum, and other physical quantities do not vary smoothly at atomic scales, but instead exist in discrete units. This concept first appeared in Max Planck's work on Blackbody radiation, and was later reinforced by Albert Einstein's explanation of the photoelectric effect. Quantization challenged the classical assumption of continuity and introduced the idea that nature has built-in limits on how physical properties can change. Another foundational concept is wave-particle duality. Classical physics treated particles and waves as entirely separate entities, but quantum mechanics revealed that microscopic objects can exhibit both behaviors. Light, long understood as a wave, was shown to behave like a particle under certain conditions, while electrons, traditionally viewed as particles, displayed wave-like interference patterns. This dual nature is not a contradiction but a fundamental feature of quantum systems, showing that classical categories are insufficient at small scales. The probabilistic nature of quantum mechanics forms another core foundation. In classical physics, the future behavior of a system can be predicted exactly if its initial conditions are known. Quantum mechanics replaces this certainty with probability. The theory does not predict exact outcomes, but provides probabilities for different possible results. This shift does not arise from experimental limitations, but from the structure of the theory itself, indicating that uncertainty is intrinsic to nature. Closely related to this is the concept of the quantum state, which contains all the information that can be known about a system. The quantum state is not a direct description of physical reality in the classical sense, but a mathematical representation of probabilities. It evolves according to precise rules, yet the outcomes of measurements are inherently unpredictable. This distinction between deterministic evolution and probabilistic measurement is a defining feature of quantum mechanics. Measurement itself plays a central role in the foundations of the theory. In quantum mechanics, the act of measurement affects the system being observed. Certain properties do not have definite values until they are measured, a radical departure from classical thinking. This led to intense philosophical debates about the role of the observer and the nature of reality. While interpretations differ, the experimental predictions of quantum mechanics remain consistently accurate. Another key foundation is the principle of complementarity, introduced by Niels Bohr. This principle states that certain properties of quantum systems, such as wave, like and particle-like behavior, cannot be observed simultaneously. Each description is necessary but incomplete on its own. Complementarity highlights the limits of classical concepts and emphasizes that understanding quantum systems requires multiple, mutually exclusive perspectives. The uncertainty principle, formulated by Werner Heisenberg, is another cornerstone of quantum mechanics. It establishes fundamental limits on the precision with which pairs of physical properties, such as position and momentum, can be known simultaneously. This is not due to experimental imperfections, but reflects the intrinsic structure of quantum systems. The uncertainty principle reshaped how physicists understand measurement, causality, and the limits of knowledge. The mathematical framework of quantum mechanics also forms part of its foundation. Classical equations of motion were replaced by new mathematical tools that describe the evolution of quantum states. These equations successfully explained atomic spectra, chemical bonding, and the stability of matter. The precision and predictive power of this framework quickly established quantum mechanics as one of the most successful theories in the history of science. Despite its success, the foundations of quantum mechanics raised deep philosophical questions. What does the quantum state represent? Is reality fundamentally probabilistic, or is there a deeper deterministic layer beneath it? Different interpretations emerged, reflecting different ways of understanding the same mathematical formalism. These debates continue today, demonstrating that the foundations of quantum mechanics are not only scientific, but also philosophical. The impact of these foundations extends far beyond theoretical physics. Quantum mechanics underlies modern technologies such as semiconductors, lasers, medical imaging, and quantum computing. Every application rests on the principles developed during the early decades of the theory, showing that abstract ideas about nature can have profound practical consequences. In essence, the foundations of quantum mechanics represent a new way of understanding the universe. They reveal that nature is not governed by the smooth, predictable laws imagined by classical physics, but by deeper principles that challenge intuition and reshape the concept of reality itself. Through quantization, probability, and wave-particle duality, quantum mechanics provides a framework that continues to expand human knowledge and redefine the boundaries of science. The lasting impact of Max Planck's quantum breakthrough on modern science and technology is profound, far-reaching, and continues to shape our understanding of the universe as well as the tools we use in everyday life. When Planck introduced the concept of energy quanta in 1900, he was primarily motivated by a desire to solve the Blackbody radiation problem. Yet, his work set in motion a series of discoveries that would transform the foundations of physics, chemistry, material science, and even information technology. The influence of Planck's insight extends across multiple disciplines, bridging fundamental theory with practical applications, and establishing the framework upon which the modern technological world is built. At the most fundamental level, Planck's introduction of quantized energy challenged the long-standing assumptions of classical physics. By demonstrating that energy is exchanged in discrete packets, he revealed that the behavior of matter and radiation at microscopic scales is fundamentally different from the smooth, continuous flows described by Newtonian and Maxwellian physics. This insight laid the groundwork for quantum mechanics, the theory that describes phenomena at atomic and subatomic scales. Quantum mechanics has become the backbone of modern science, providing explanations for atomic structure, chemical bonding, nuclear interactions, and particle physics. Without Planck's initial step, much of 20th century physics, from Einstein's photoelectric work to Schrödinger's wave mechanics, would not have been possible. In chemistry, the impact of quantum theory is particularly profound. The structure of atoms and molecules, the nature of chemical bonds, and the behavior of electrons are all governed by quantum principles. Quantum mechanics explains why atoms combine in specific ways, why molecules have particular shapes, and how chemical reactions proceed. Planck's discovery of energy quantization directly led to the Bohr model of the atom, which introduced discrete energy levels for electrons. Later, quantum mechanics refined and generalized these ideas, enabling chemists to predict reaction pathways, electronic configurations, and spectroscopic properties with remarkable accuracy. Modern fields such as quantum chemistry and computational chemistry rely entirely on these principles to design new materials, drugs, and catalysts, demonstrating a clear line from Planck's abstract insight to practical applications. In physics, the impact of Planck's work extends to multiple areas, including condensed matter physics, particle physics, and astrophysics. Quantum mechanics explains the stability of matter, the behavior of semiconductors, superconductivity, and magnetism. Technologies such as transistors, integrated circuits, and solid-state lasers, all central to electronics, depend on an understanding of quantum behavior in materials. In particle physics, the quantization of energy and the wave-particle duality concepts that stem from Planck's work underpin the Standard Model, which describes the fundamental particles and forces of the universe. Astrophysics, too, benefits from quantum theory. Phenomena such as stellar nucleosynthesis, Blackbody radiation from stars, and the cosmic microwave background are analyzed and understood through the lens of quantum mechanics. One of the most visible technological impacts of Planck's breakthrough is in the field of electronics and computing. The development of semiconductors, transistors, and microchips, all essential to modern computers and smartphones, relies on a deep understanding of quantum behavior. Electron energy levels, band theory, and quantum tunneling are phenomena that can only be explained through the principles that originated with Planck's quantization. Without these insights, the digital age as we know it, personal computing, the Internet, and smartphones, would be impossible. Quantum mechanics not only enabled these technologies, but continues to push the boundaries with quantum computing, which exploits superposition and entanglement to perform calculations far beyond classical limits. Medical technology is another domain profoundly influenced by Planck's work. Imaging techniques such as magnetic resonance imaging MRI, X-ray spectroscopy, and PET scans all rely on quantum principles. The interaction of energy with atoms, the behavior of electrons in magnetic fields, and the emission and absorption of radiation, all areas rooted in Planck's initial insight, are central to these tools. Modern medicine increasingly relies on technologies that are direct applications of quantum theory, affecting diagnostics, treatment, and research in ways unimaginable before the 20th century. Communication and energy technologies have also been transformed. Lasers, which depend on controlled energy transitions between quantized states, enable fiber optic communication, barcode scanning, surgery, and precision measurement. Solar cells rely on the photoelectric effect, explained by Einstein using Planck's constant, to convert light into electricity efficiently. Quantum dots, superconductors, and photonic devices, all crucial to modern technology, depend on understanding and manipulating quantized energy levels. Planck's insight into energy quantization thus became the key that unlocked a new world of possibilities in applied physics. Moreover, Planck's work has had profound philosophical and conceptual impacts. By showing that energy is quantized, he initiated a paradigm shift in how scientists think about nature. The deterministic world view of classical physics gave way to a probabilistic understanding, where uncertainty and discrete interactions are fundamental. This shift influences not only science but also technology, guiding how engineers, physicists, and chemists approach problem solving. The design of experiments, the interpretation of data, and the development of new technologies all incorporate the lessons learned from quantum mechanics. Education and research have also been shaped by Planck's legacy. Quantum mechanics is now a cornerstone of science curricula worldwide, training generations of scientists to think in terms of probabilities, discrete energy states, and wave-particle duality. Advanced research in nanotechnology, quantum optics, and quantum information science all build upon the principles that originate with Planck's introduction of energy quanta. His work provided a universal language that connects disparate fields, from material science to cosmology, enabling interdisciplinary innovation. Finally, the lasting impact of Planck's discovery is visible in the ongoing revolution of quantum technologies. Quantum computing, quantum cryptography, and quantum teleportation are no longer theoretical curiosities. They are emerging as transformative tools in computation, secure communication, and information processing. All these advances trace their origins back to Planck's recognition that energy is fundamentally quantized. Without his courage to propose a radical idea in response to the Blackbody radiation problem, the modern landscape of science and technology would be unimaginable. In conclusion, the lasting impact of Max Planck's quantum breakthrough on modern science and technology is unparalleled. By introducing the concept of energy quanta, Planck laid the foundation for quantum mechanics, reshaping our understanding of the natural world and enabling countless technological innovations. From chemistry and physics to computing, medicine, energy, and communication, the principles that arose from Planck's work continue to guide research, fuel technological progress, and redefine human capability. His discovery transformed science from a framework based on continuity and determinism to one that embraces discrete interactions, probability, and the fundamentally quantized nature of reality, and enduring legacy that shapes the world to this day.